All right, welcome to MECH1320. We're going to go ahead and get started. We're going to start with Chapter 1 and get into Chapter 2, kind of kill two birds with one stone here. So Chapter 1, we're going to start with maintenance, talk about what is maintenance and understanding maintenance, okay? And then we're going to talk in Chapter 2 just a little bit about safety and how that kind of works. We're not going to get into, great depth with it, but just kind of some general safety practices that you're going to want to be able to go through and understand, and those will vary kind of per company that you're in as well. So each company will kind of have its own. Okay, so let's talk about different types of maintenance techniques, all right? We have preventative maintenance, we have predictive maintenance, and we have proactive maintenance, okay? So when we talk about preventative maintenance, okay, those are scheduled and unscheduled tasks on equipment, all right, that we can optimize it and prevent any type of future failure, or just want to keep it going. So you're changing the oil in your vehicle or something along those lines, right? That's preventative maintenance, so that your engine doesn't blow up on you or that sort of thing, keeping everything well lubricated. So that's preventative. We don't want anything to break down, so we're going to constantly change the oil, make sure that it's clean of contaminants, and do those sort of things. So just an example how you can kind of relate to your house. If we have predictive maintenance, okay, that's where we monitor the condition of the equipment so that we have like a baseline or how the equipment should normally, be operating, and then we can tell, oh, it shouldn't be operating like that. So predictive maintenance, something might go wrong. So like, maybe it's your house, you have your wash machine, and you put a bunch of stuff in it, that's heavier, like towels, and you'll kind of hear, the wash machine sounds kind of funky and things like that. Let's go check it out before, it really gets like off balance and destroys some things. So, it sounds like it's off the norm. You have too many towels on one side or something like that. So, you monitor it, or you're monitoring temperature on something. You see as, why is the temperature all of a sudden fluctuating and going up and those sort of things. So, let's shut it down and see what's going on. So, where are we to the baseline where this machine should be operating versus, where it's at right now. So we can predict, something might go wrong, we need to do this, okay? Proactive maintenance, all right? That's, making things on time, checking equipment as we should be, so when it says that you need to take a look at an engine or something after it's ran a certain amount of time, so that you're constantly, taking care of that. You're checking a chain, to make sure there's any nicks, burrs, dents, things like that. You're kind of always checking, fluid levels, just like you'd check your the oil in the engine of your vehicle or things like that. So battery maintenance, okay? So if you have a battery, maintenance battery, we don't have too many of those anymore, but, making sure that you're checking the levels and those sort of things. So that's kind of the difference between, preventative maintenance, proactive maintenance, where you're constantly always checking, monitoring, making sure everything's good, inspecting the belt touching, predictive maintenance, all right? Where are we compared to our baseline, all right? Or preventative, right? Doing our everyday scheduled, things. It's been this many, rotate your tires so they last longer, those sort of things, all right? But that'll relate to different equipment and industry, as you go through those sort of things, okay? So, if we take a look in depth at more examples here, vibration analysis, okay? So we have a motor, so, we can predict that, all right, this motor's like, shaking way more than it normally should, all right? What's wrong? What's off center? Things like that. So, that's where I talked about the wash machine a little bit before. You had too many towels on one side, so it's spinning. It doesn't sound good, okay? But we can do analysis, so there's different sensors and things that can kind of tell us, if it's rotating motion or something is off kilter for us, okay? We have oil analysis, so we can see, if we are changing the oil in something and we find different types of particles or things like that, is there corrosion in the system? Is it starting to break apart? Are there chips of metal or things like that? So you can constantly, check the oil to make sure everything's clean in there. We can also do thermography, so we can take a look at the temperature of equipment, all right? And we know what it should be operating at certain temperatures versus what it shouldn't be. So we can kind of see all right, this is way hotter than it needs to be or where it's normally operating. Something's not working right here. So, just kind of being able to gauge and being able to use different tools at your disposal to predict when something, might break down. You can't foresee everything, but it's the idea of, monitoring it to that baseline, okay? So if we step even deeper in, right, we're talking vibration analysis. We're looking at the resonance, okay, the magnification of the vibration, right? Something, motors operate at a normal frequency or things like that. But if something, happens and there's, an extra load on the motor, okay, it's not going to move around as fast or things like that. Or, something becomes loose and the motor starts to shake, okay, different things like that. So we look for different things like the critical speed, okay? That's the critical speed. That's the speed at which that mechanical part naturally resonates, okay? And starts, it could go one way or the other from there, but that's the critical speed, okay? We take a look at its cycle, its amplitude, and those are what we looked at in the electrical class when we look at cycle and amplitude and things like that, right? We know that when we're talking about vibration analysis, we're looking at a sinusoidal type wave, all right? So we can see some sort of pattern, is it out of the norm? And, is the frequency changing, right? Remember, frequency is cycles per second. We talked about that in hertz and that sort of thing. Or the phase, okay, has it shifted, as it's rotating around? Or, has the velocity or the speed and the acceleration changed? So those are all different mechanisms that we can use to kind of read vibration analysis. And we have a bunch of different sensors and equipment that are going to constantly give us, feedback in a system so that we can monitor that. You're not standing there doing it, okay? But, we use transducers and analyzers. Essentially, what a transducer is doing is it's taking whatever we're analyzing it and turning it into an electrical signal, okay? So whatever we're using to to read the vibration of the motion, we're converting that into an electrical signal so that it turns it into like a sinusoidal wave or something. And based on that waveform, we can put it into something that analyzes that waveform and this goes back to, how is that motor or whatever we're looking at operate in normal conditions and how's it operating now? So it can do a comparison, and based on that comparison, it can send an alert signal to us. Hey, something's off here. Something's wrong with, this particular motor, this conveyor, or all the different things. It doesn't just have to be those, but those are common things that oscillate, make vibration. All right, so let's take a look at an example here. If we have two different beams going on here, we have two vibrating cantilever beams. Say they had the following waveforms, okay, and then we'll go through a couple questions about them. So if we take a look at what the beam is doing, all right, hey, this is kind of the same thing as, like earthquake analysis or things like that, as well. So this is how we develop and understand, the Richter scale. Now, it's on a logarithmic scale, but, based on the oscillation of the earth and things like that, we can convert it to a number, okay? Same kind of thing here. If we're taking a look at vibration of beams as such, okay, and its displacement, right? So when we're talking vibration, we're talking about something, shaking up and down. So it has its center point, and how far is its amplitude, remember, how far it is from that center point that we talked about in electrical. So if we have these two different waveforms here, all right, we've got, this blue wave, and we've got the red wave as we're looking here. Now, if we look at this, just before we even get to the questions, we can see that they have the same amplitude, okay? But what's different for them is the frequency or the cycles, right? We can just look at this and we know that that blue wave is happening much faster, all right, than that red wave. So what is the frequency of the blue wave? Remember, frequency is how many times something happens per second. Okay, so how many times does that waveform complete in 1 second? So you'll just count, how it goes through. So if you start at 0, okay, it goes up to 2, down to -2, goes through 0.5, goes up to 2, all right, down to -2, and then it goes back up at 1. So that waveform happens twice in 1 second, all right? So remember, that's 2 cycles. So when it goes from negative to positive and recurs back at that center point, okay? So we have 2 cycles, and remember when we're talking about frequency, we talk about in hertz, all right? So it's cycles per second, all right? So in this case, ends up being 2 hertz. But remember, you know, I just said start at 0 and 1. You can pick any place on here to do this, okay? You can pick any place on here to do this. So if we take a look at 2.5 and 3, we can do that, okay? There's only 1 cycle there, so that doesn't complete everything, right? And it's not 1 second either, okay? So we can do it that way, and if we do it that way, we're going to say that frequency is 1 cycle over 0.5 seconds. So you don't have to always use a second. It doesn't always gauge for you. But in this case, we can use a half a second. So you can say 1 cycle divided by 0.5, or 1 cycle divided by 1/2 gives us 2. So in your calculator, if you do 1 divided by 1/2, you get 2 cycles per second, and it's 2 hertz. So there's 2 ways of analyzing this, right? You can count how many times the wavelength happens in 1 second, or you can take 1 period, right, from anywhere on here, 2.5 to 3 or 1.5, to 2, 1 complete period. Remember where it starts to finish, okay? And you're going to take that and divide it by how long that is, okay? So 1 period, in this case, takes a half a second. 1 divided by 1/2 is 2. Or we can count the amplitudes, the number of times that it occurs in 1 second. Either method works. We get the same answer, being 2 hertz. Okay? So, next, what's the frequency of the red wave? Okay, well, how long does it take for this guy to complete 1 cycle? So 1 cycle, if you're looking at this, it takes 2 seconds for that wavelength to complete 1 cycle. Okay? So when we do it this case, all right, X's mark the spot, you're going to have 1 divided by 2, which is 0.5 cycles, which ends up being 0.5 hertz, or we say half a hertz. Does this make sense if we look at this, right? The blue wave, right, is traveling much faster than the red wave. So hence, it should be the higher wave, right? The blue wave is 2 hertz. The red wave is 0.5 hertz, or half a hertz. It is slower. Half a hertz is slower than 2 hertz. So what we've analyzed does make sense here. Okay, so there's kind of how we can take a look at the waveform, analyze it, and this, kind of follows up with what we did in the electrical class, but we're just kind of, revisiting some of those things here. All right, so let's take a look at another example here. We have 1 beam that started vibrating at frequency F1. A little while later, another beam started vibrating. The waveform graph of the 2 beams, right, is going to be shown below. Assume that there's no dampening that occurs, all right? There's nothing to, kind of reduce the amount that it's vibrating, or things like that. So if we took the 2 waveforms again, once again, we are going with blue and red waveforms, okay? And so which waveform belongs to the first beam? All right, we got a blue waveform, and we have a red waveform. Well, we got to go back to understanding the reading. It says 1 beam started vibrating at a frequency F1. It says a while later, another beam started vibrating. So that would be which one here, all right? The blue waveform, okay? That's the first beam. The one that started a little while later was the red beam, okay? So the first waveform belongs to the blue wave. The second one that started later, right, is the red one, because we can see that from 0 to 0.2, there was a 0.2 second delay between the 2 waves, okay? So what's the frequency of the blue wave? Why don't you pause it in the video and see if you can figure that piece out. Remember, we're basing it on 1 cycle here. So if we take a look at 1 cycle of the blue wave, all right, 1 cycle lasts 0.8 seconds, okay? So we have to take 1 divided by 0.8, so we're going to get 1.25 hertz, okay? So make sure that you're going along and that you get that calculation. The frequency of the red waveform. Well, the red waveform, if we take a look at it, we can say that it starts at 0.2 and completes at 1. It still has the same amount of time, okay? It's still taking 0.8 seconds for that red wave to complete 1 cycle. So it's going to be the same, 1 divided by 0.8, so we get 1.25 hertz, all right, on that other waveform. what's the phase difference between the two waves? Okay, the phase, right? Well, what are we talking about there? Since they start at different times, there's a shift, okay, and we call that the phase shift. If they were in phase, the red wave and the blue wave would be on top of each other, right? If they were in phase, they would be the exact same waveform. But since the red phase has a delay in it, okay, there's a phase difference between that, and we can clearly see that it's 0.2 seconds. The red wave starts 0.2 seconds later than the blue wave. And revisiting some of our electrical stuff again, what's the peak-to-peak amplitude vibration of the beams, right? How high does it get? How low does it get? And that difference. So it goes from -2 all the way up to 2. Okay, they don't cancel each other out. That's a total of about 4 inches, right? When that wave's oscillating, it goes, 2 inches above its center line, and it goes 2 inches below its center line. So the total distance that that beam is vibrating, okay, is 4 inches. Now that's huge for a beam, all right? Our building's going to wreck if we got something like that going on, okay? All right, that's kind of it for Chapter 1. We're going to step into Chapter 2 here, and we're just going to briefly, talk about different things, accidents, accident prevention. That's the whole reason that we have safety procedures in play, all right? Accidents do happen in the workplace. A lot of workplaces keep track of, how long they've been accident-free and that sort of thing. But there's a lot of safety in place, to make sure we don't have accidents. One reason, right, you wear a hard hat sometimes. So that's because you might hit your head on something. So in order to prevent that accident, all right, from hurting yourself by hitting your head, you're wearing a hard hat. You're grinding something down, you're cutting something, you're in a mill, right? There's stuff in the air, stuff can fly around. You're going to wear safety glasses, all right? You're cutting wires, they make you wear safety glasses. So, we can prevent an accident and you accidentally losing your eye or getting poked out, okay? So there's a lot of those that came into effect, all right? But for the most part, all throughout industry, they've been working for years without a lot of that stuff. But in 1989, things kind of really took, control as far as, OSHA and those sort of things, making sure that your work environment is safe. So lockout tag out became kind of the standard, and we do that with our electro and our pneumatic and hydraulic type systems so that nothing can happen when you're working on it. Nobody really wants to work on live 480 volt electricity, 3-phase, that's going to hurt if you accidentally do the wrong thing. You're not going to want to climb under some hydraulic press to work on it, if it's on. So different ways to, make sure that it's off and make sure that it stays off, that no one can remove it, all right? So we've come up with the lockout tag out. So the whole point is, we have a device on there that locks out the energy isolating device. So no one can come by and just flip on the power while you're working on it, all right? We want to be able to control all the hazardous energy sources, whether it's electrical, whether it's pneumatics, hydraulics, all those different things. And then we have a tag out, okay? So the lockout physically prevents, electricity from flowing or fluid power from flowing. The tag, all right, that lets people know and identify who put the lock on it and who the lock belongs to, and that way oh, that person's working on it, okay? So for us in our lab, okay, we're going to simulate that every time we work on a motor and we do our belt drive, our chain drive, and our gear drive in here. We are going to do lockout tag out. Now, I'm not going to make you go through with the full tag out. You don't need to write everything down on it. But when you guys are working in groups, you're going to put the hasp on, all right? So that's the clip there with the red handles that the lock is going through, and you're going to put a master lock on there. And each one of you will have a lock. So part of the lockout tag out procedure is each person has their own lock that is working on that machine, all right? Because you don't want one lock for 2 guys, and one guy takes his lock off and goes to lunch, right? Well, the other guy is just sitting there working, and someone can come and energize the system and hurt you. So it's imperative, all right, that we can't power up the system until everybody's lock is off of it, okay? And it's your key, and you're the only one that can take that lock off. So sometimes you might do a lockout tag out, and your shift ends, and you leave it on, and you're still working on it, all right? they might call you up in the middle of the night and ask you to come take your lock off because it's you. No one else can come, cut it and take it off. It belongs to you. You are the sole responsible person there. Okay, your manager might be able to do something like that for you. Kind of depends on, where you're working, but it's very imperative. So that saves a lot of lives there. Okay, so that's what a lockout tag out looks like. All right, that lets people know, don't energize this system. Someone's working on it, or it's waiting for maintenance. We don't want it to work because it could be hazardous to what's going on. Okay, so lockout sequence. Now, it might be different where you work. This is a general sequence, that, companies go through. But you'll know based on your company where you work, what the procedures are. All right, so a general rule of thumb, notify all the employees that are affected, right? Hey, we're shutting down the line, or these sort of things. Or, hey, we're going to work on this for a little bit so you won't be able to walk across or do this sort of thing. Okay? Now, the lockout, it has to identify the machine load energy. So you have to make sure every possible way for that to energize is shut down. Sometimes there's redundant power. Sometimes there's controls coming from a different source and those sort of things. Make sure you shut down the equipment properly, all right? Don't be using e-stops and that sort of thing. Make sure it goes down through its normal shutdown procedure. Sometimes, right, it is an emergency, though, you have to hit e-stop. But if it's just a general maintenance or repair or those sort of things, follow the regular procedure for shutting it down. Deactivate the energy source. Lock it out, right? You're putting the hasp through it. So we can look at the top picture there that we had on the previous slide. All right, putting the hasp through it so no one can flip the switch up, and you're putting a lock on it so that no one can remove that hasp. All right, so you've officially locked out the energy. All right, make sure that you dissipate any stored energy. Like capacitors, right? Their whole job is to store energy and dissipate when called upon. So make sure that you discharge those, because if you touch those live, all right, that could hurt. Make sure the equipment is disconnected and can't operate. Try to operate the equipment. All right, push the buttons, see if it'll start up. Okay, make sure that it is completely dead. All right, once you've locked it out. Okay, different requirements. Okay, so use a positive means to keep the energy isolating device in the safe position. That's why we use a lock and a hasp. Okay, that device itself has to withstand whatever elements it's in. Okay, excessive heat, freezing, radiation. All right, all those different kinds of elements that it might be exposed to, it has to be able to stay locked in all of those. Okay, it has to be standardized in the facility, which means everybody in the facility is using the same lockout tag out procedure, using the same kinds of locks. Some companies, they put your picture on your lock and those sort of things. So it just kind of depends on where you work. Okay, the lockout device has to be strong enough to prevent removal without excess force. I mean, really the only way you're getting through that lock is with bolt cutters. No one can come along there and pull it off and that sort of thing. Okay, so also make sure, you notify employees before the application and removal of it. So let everybody know that's working. Hey, we're locking this out. It's going to be down for maintenance, down for 20 minutes, sort of things. Hey, we're bringing this back online, because they knew that you were locked out, tagged out, but they might have said something over there. They might have been in the vicinity. They could be in a dangerous location, different things like that. So make sure that you're giving people an alert. Hey, we're systems firing back up. Okay, and the most important thing, and I've already hit on this before, the only employee that can take the lockout tag out off is the employee who applied it. Only you can take off your lock. Only you have the key to your lock. Okay, so yeah, I know in certain companies it may be a little different or things like that, but this is just in general kind of how it goes through. And very important safety when we're talking about mechanical devices that can crush you, hurt you, tear you. And do those sort of things. Tag out, we see lockout tag out. Sometimes the person's information's on the lock and that sort of thing. Tag out, we use those for pneumatic devices, all right? So you can push through, we've talked about on the 870 trainer and things like that. And you can tag it out by, using a zip tie or the tag through it. So, or you put the lock on the pneumatic piece so that air can no longer go through there. Okay, it has to state clearly why that energy device is not allowed. Okay, it's got to be placed and a lock would be placed, all right? So you're not going to necessarily put a master lock on it, but you're going to put the tag there, so that's tagging it out. And you want to make sure that it's obvious so that anyone can tries to operate the device can see that it's obviously tagged out. That tag has to withstand the elements. Generally, they're like a heavier duty type of plastic tag or paper that's coated and things like that. So, if it's outside and it's raining, so it gets wet and doesn't get destroyed or things like that. Generally, OSHA, right, we want to make sure that it's standardized throughout the facility, and they want a non-reusable type of attachment. That's why we don't do the tag outs in class, because I don't want to buy a bunch of those, every year for us just to write a name on and throw away. Okay? It just doesn't make sense for us on that. But it should be a non-reusable type of attachment for the tag out. So you're going to read pages 27 and 28 of the text as well for a little bit more fun information on lockout, tag out, and any other safety procedures. But those are what we're going to be using in the classroom on the mechanical trainers and things like that. So just to give you a heads up. All right, well, that is the end of Chapter 1. Chapter 2, email me if you got questions or anything along those lines. Else, I'll see you in class, see you in lab. All right, have a great day.